Hello friends. So today we are going to solve three questions, and these three questions were asked in the year 2002, 2003, and finally it is from year 2005. So in the first question, which were asked in the year 2002, and we are given a metal bar AB can slide on two parallel thick metallic rails separated by a distance L, a resistance R, and an inductance L are connected to the rail as shown in figure. A long straight wire carrying a constant current I0 is placed in the plane of the rails as shown. The bar AB is held at rest at a distance x0 from the long wire. At t is equal to 0, it is made to slide on the rails away from the wire. So answer the following questions. So we have here three questions that were asked based on this entire description. So in the first, we are supposed to find out the relationship among I, di by dt, and d phi by dt, where I is the current in the circuit, phi is the flux of the magnetic field due to long wire through the circuit. In part B, it is said that it is observed at time t is equal to capital T, the metal bar AB is at a distance 2x0 from the long wire. The resistance R carries a current I1. Obtain the expression for the net charge that has flown through the resistance R from time t is equal to 0 to time t is equal to capital T. And in the C part, it is asked the bar is suddenly stopped at time t. The current through the resistance R is found to be I1 upon 4 at time 2t. Find the value of L upon R in terms of other given quantities. So we have this figure in which a wire is there which is carrying a current I0, and there is a sliding bar AB, and it is at particular time it is at a distance x0. Okay. So we are going to solve first of all part A. So in part A, we are supposed to find out a relationship between current di by dt and d phi by dt. So it is given that the metal bar AB slides on the two parallel rails in the presence of magnetic field due to this current carrying conductor. Okay. So this current carrying conductor will generate a magnetic field, let us suppose that is B, and because of that you can say this rail AB is going to slide. Therefore we can write it as that metal bar AB slides on two parallel rails in the presence of magnetic field, due to long straight wire carrying a constant current I0, carrying a constant current I0. So in this particular question, the magnetic field is not given directly to us, but that is given based on the current that is being carried out by this long straight wire. And secondly, as the bar is going to move away from the wire, the magnetic field B at the bar's position is going to change. So obviously there will be induced EMF in the circuit. So you can say as bar moves away from wire, the magnetic field let us suppose that is given as B at the bar's position changes, inducing an EMF, which let us suppose is given as E. And at one particular time it is given that the bar is at a distance x from the wire. Therefore we can write the magnetic field at a distance x from the wire. The magnetic field at a distance x from the wire. So we can write it as magnetic field B, which is dependent upon x, will be equal to mu naught I naught divided by 2 pi x. Now we can find out that as it is going to slide, there will be current induced in the circuit. Okay, so let us find out the current direction. So the magnetic force acts on the free electrons along the negative y-axis, and causing electrons to move from end A to end B, causing the electrons to move from end A to end B. So therefore end A becomes positive and end B comes as negative. Therefore current flows from B to A in this moving rod. Therefore current flows from B to A in the circuit, and the circuit consists of inductor R and L, and it is given that the circuit consists of R and L. So we can use KVL. Therefore by KVL we can write the equation induced EMF E minus of R minus L di upon dt will be equal to 0. From here, induced EMF is equal to IR plus L di upon dt, and the induced EMF E is nothing but our rate of change of flux. So this gives us that d phi upon dt is equal to IR plus L di upon dt. So this was our first part, relationship between all the three parameters. Now we come to the part B. In part B, we have to find out the net charge that flow through resistance from time t is equal to 0 to time t is equal to capital T. So we are going to start with this equation, and we can modify it a little bit. We can write this as d phi is equal to Ri dt plus L di upon dt multiplied by dt. So here dt and dt cancels out. So we get our d phi is equal to Ri dt plus L di. Now we integrate both sides for the given time duration, that is t is equal to 0 up till t is equal to capital T. So we can write this as phi of 0 up till phi of capital T, and we can write this as from 0 to capital T, and here we write at current as 0 and current at capital T. Now the integration of current over the entire time will be giving us a charge, total charge rather. So we can say integration of 0 to t of I dt will be giving us total charge Q, and if we assume that the initial current is 0, so I of 0 equals 0, and final current is given as I1, therefore we can write this equation will be written as phi of capital T minus phi of 0 will be equal to RQ plus LI1. And now it is simple calculation, we can solve it for Q. So Q gives us this as flux at time t minus flux at time when is 0 minus I1 divided by R. Now we are going to find out the flux. Solve for flux part. Okay. So we can say the calculating change in flux. Calculating change in flux. So it is given that the bar moves from x is equal to x naught to x is equal to 2x naught. So given as the bar moves from x is equal to x naught to x is equal to twice x naught, therefore flux phi will be equal to x naught 2x naught magnetic field dependent on x multiplied by L dx. And we already know the value of this B, so we can write this as x naught 2x naught this is mu naught I naught divided by 2 pi x, and this is L dx. So we can just solve it. We are going to get this as rest of thing will be constant, and we are left with only integration of this 1 upon x, so which will be natural log of x, and by substituting we can easily solve it. Therefore we can say our phi will be equal to mu naught I naught L upon 2 pi natural log of 2x naught divided by x naught, and x naught on x naught cancels out, so this comes as mu naught I naught L upon 2 pi, and this is natural log of 2. So we get the change in the flux. The change in flux means this particular value. So we can write that our charge Q is equal to, this is our mu naught I naught L divided by 2 pi natural log of 2 minus, and this was our Li1, and divided by R. And if you require, we can just further solve it. So we can say that the charge Q will be equal to, we have it as mu naught I naught L divided by 2 pi R natural log of 2 minus L upon R, and this comes as I1. So this is our charge. And next we are going to find out that the current decay, value of the current decay in the inductor. L upon, value of L upon R we have to find out value of L upon R. So we come to part C. So it is given that at t is equal to capital T, the bar is stopped. Bar is stopped, and along with this, the circuit, it behaves like a series LR circuit. LR circuit having a current I1. Having current I1, and the current will be now exponential decaying current because bar stopped to move. So you can say the current decays exponentially. Current decays exponentially. So we can write for a series LR circuit with a current I1 which is decaying exponentially, we can write this as I of t is equal to initial current I1 e raised power minus R upon L, and this comes as T minus capital T. And it is given that at time at t is equal to capital T, current is I1 by 4. So we substitute the value. You can say that I of t will be equal to I1 by 4 at t is equal to capital T, 2t's rather. So we substitute the values, we get this as I1 by 4 will be equal to our I1 e raised power minus r upon L. This comes 2t minus capital T, and which can be written as our I1 e raised power minus r upon L multiplied by capital T. And here I1 and I1 cancel out. So we get 1 upon 4 is equal to e raised power minus r upon L t. So it can be written as, if we take natural log both sides, natural log of 1 by 4 is equal to minus r upon L times t. Now it is a simple calculation. We get this as minus natural log of 4 is equal to minus RL upon T. This minus and minus goes away, and we are supposed to find out L upon R. This comes as T upon natural log of 4. So this is our ratio of L upon 4 that was asked in the question. Now we come to the next question that was asked in the year 2003. And in this question, it is given that two infinitely long parallel wires carrying currents I is equal to I naught sine omega t in opposite directions are placed at a distance 3a apart. A square loop of side A of negligible resistance with a capacitor of capacitance C is placed in the plane of wire as shown in the figure. Find the maximum current in the square loop. Also sketch the graph showing the variation of charge on the upper plate of the capacitor as a function of time for one complete cycle, taking anti-clockwise direction for the current in the loop as positive. So we have two wires. Let us call that as this as wire 1 and wire 2. Both are carrying same current, but directions are opposite to each other. The distance between the two wires is 3a, and between the wire we have a square loop whose dimension is given as a. So it is placed equidistant from both the wires of these respective parallel lines. So we are supposed to find out the maximum current in the square loop, and we have to sketch the graph, variation of charge in the plate of capacitor as a function of time. So we have to find out two things. First is the variation of the current, maximum current rather, and the waveform of the charge. So in the question, we are given that there are two infinitely parallel wires. So we have two infinitely parallel wires, and the current in both is given as I naught sine omega t in opposite direction. In opposite direction, and the separation between the wire is 3a. Wires are separated by 3a. So first of all we are going to start with the magnetic field due to the wire, and the standard formula we already know, that B is equal to mu naught I upon 2 pi r. So you can say magnetic field due to wire at a distance r, carrying a current I, it is given as B is equal to mu naught I upon 2 pi r, and the current is flowing rather in opposite direction. So we have two wires, and the net magnetic field will be the addition of the individual magnetic field inside the wires. So what we do, we consider a small segment, that is dx, of the, you can say, loop. Okay. So in this case, let us consider this is our left wire, and we have a square loop, and in this square loop we consider a small segment whose width is dx, and this segment is at a distance of x from this left wire. So the distance from the right wire will be 3a minus x. And the direction of current, downward and upward. So here it is downward and this is upward. Okay. So what we do, we write it that consider a small segment of width dx on the loop. Secondly, you can say at a distance x from left wire. So you can write that the distance from right wire will be equal to 3a minus x. So the net magnetic field will be individual magnetic field and there is sum. So if the magnetic field generated by left wire is B1, and because of the right wire is B2, then the magnetic field at the segment will be B1 plus B2. So we can say the magnetic field at the segment let us suppose that it is given as B, then B will be equal to mu naught I upon 2 pi x plus mu naught I upon 2 pi 3a minus x. This is because of left wire, and the second is for the right wire. Now we can find out the flux through the segment. Flux through the segment. So if we say the flux through the segment is given as d phi, then we can say our d phi will be equal to B, and this is multiplied by area, and this comes as B A dx. We substitute value of B, that is mu naught I upon 2 pi x plus mu naught I upon 2 pi 3a minus x multiplied by a times dx. So we make slight adjustment in it. You can say our small flux will be equal to mu naught Ia divided by 2 pi, and this comes as 1 upon x plus 1 upon 3a minus x times dx. Now we can find out the total flux through the loop. Total flux through the loop and the loop extends from x from A to 2A. So this is our A and this is our 2A. Total flux of loop. So we know the loop extends from x is equal to A to x is equal to 2A. Therefore, total flux phi will be integral of d phi, and this gives us mu naught Ia upon 2 pi integration A to 2A 1 upon x plus 1 upon 3a minus x, and this comes as dx. So here we have two integrations. Let us call this as first one and this is as second one. So we will be taking them one by one. So we have first will be equal to integration of a to 2a 1 upon x dx. So this will be natural log of x. Natural log of x, we have here natural log of x from a to 2a giving us natural log of 2a minus natural log of a, and which comes out as natural log of 2a divided by a. Here a and a cancels out. This gives us natural log of 2. Second part, which is of integration from a to 2a 1 upon 3a minus x dx, and this comes as minus natural log of 3a minus x, and from a to 2a we substitute the value. This comes as 3a minus 2a, so this comes as natural log of a minus natural log of 2a, and we can just simply solve it now. This will be our minus natural log of a plus natural log of 2a, and once again this will be our natural log of 2a by a and a cancels out, so this comes as natural log of 2. Therefore, we can write that our flux phi will be equal to mu naught IA divided by 2 pi, and this is our natural log of 2 plus natural log of 2, and this will be our twice natural log cancel with this 2, and we can write this as phi is equal to mu naught IA upon 2 pi multiplied by twice natural log of 2. 2 and 2 cancels out, and this gives us mu naught IA upon pi and natural log of 2. So this is our the flux, but we have value of current also is given to us. So we are given that I is equal to I naught and sine omega t. So we can substitute it. This gives us that our flux phi will be equal to mu naught I naught a natural log of 2 divided by pi, and this comes as sine omega t. So this is our flux, and we are supposed to find out the charge. So first of all, we are going to find out induced EMF, and that will be our negative derivative of this value of flux. You can say that induced EMF will minus d phi upon dt. So we derivate this equation, we get minus, and this will be equal to our mu naught I naught a natural log of 2 divided by pi, and this comes as omega multiplied by cos of omega t. Now charge on the capacitor. Now this induced EMF, it will be nothing but the voltage across the capacitor. So we start with our final part, that is charge on capacitor. Charge on capacitor. So you can say the capacitor voltage is equal to EMF. Capacitor voltage is equal to the EMF, and which will be our, from here we can write it as that V will be equal to EMF, and that is equal to Q upon C. Therefore, charge over Q for any time t will be equal to capacitance multiplied by the induced EMF. This comes as minus, and we have this as mu naught I naught a omega c natural log of 2 divided by pi, and this comes as cos of omega t. So this is our charge. Now easily we can find out easily the current. Current is nothing but the derivative of the charge. You can say current in the loop. Current in the loop. So we can say our I of t is equal to dq by dt. So we get this as mu naught c I naught, and we have a natural log of 2 divided by pi, and this comes as omega square, and we have here sine of omega t. And we have to find out the maximum current. So maximum current will be dependent upon this sine of omega t. If its value is 1, we are going to get the maximum current. So you can say maximum current for sin omega t is equal to 1. So we can write our I max will be equal to, this is our mu naught C I naught A omega square natural log of 2 divided by pi. And we have to find out the charge on the upper plate. Charge on the upper plate, let us call that as Q upper for time t will be equal to minus of the Q of t, and Qt we just found out is our this, so this will be coming as minus of Qt, so it comes as mu naught C I naught omega natural log of 2 divided by pi, and here we have cos of omega t. And we are going to find out now the graph. And graph is quite simple. It will be simple because it is more or less dependent upon the cosine function. So therefore you can draw the graph. It is going to have a maximum value of plus Q naught and minus Q naught. So it will be, the graph will be something like this. And this will be over pi by omega, this will be over 3 pi by 2 omega, and we get this will be our 2 pi by omega, and this point will be our pi by 2 omega, and this is our time t, and in this direction we have charge q. So this was our second question, and now we come to our final question, which was asked in the year 2005. And in this question it is given a long solenoid of radius a, the number of turns per unit length n is enclosed by a cylindrical shell of radius r. Thickness is d, where d is very much smaller than r, and the length is L. A variable current I, given as I naught sin omega t, flows through the solenoid. If the resistivity of the material of the cylindrical shell is rho, find the induced current in the shell. So we are given a figure, and in this figure we have a long solenoid whose radius is a. So this is our long solenoid whose radius is given as a, and it is enclosed by a cylindrical shell rather, and whose thickness is d. So this is our cylindrical shell. And the current is given, which is flowing through this solenoid, is our I is equal to I naught sin omega t, and we have to find out the induced current inside this shell. The resistivity is given as rho. So first of all, we are going to start with the magnetic field inside the solenoid. so which is a standard formula. Magnetic field inside the solenoid, and if that is represented as B, so B will be equal to mu naught n times I, and here I is given as I naught sine omega t. So therefore we can write our B will be equal to mu naught n I naught sine omega t. Now because of this magnetic field, we can find out that the flux through the shell. Flux through the shell. So we are given that the shell, or rather cylindrical shell, encloses the solenoid. We are given that cylindrical shell encloses the solenoid. Therefore, the magnetic flux phi through the shell, because of the magnetic field B through the shell, is the product of magnetic field and cross-sectional area of the solenoid. Through the shell is the product of magnetic field and cross-sectional area of the shell. Cross-sectional area of solenoid. And we can write the formula that a flux time dependent will be equal to magnetic field time dependent multiplied by area, and magnetic field we already know is our mu naught n I naught sine of omega t multiplied by area, which is our cross sectional area, that is pi a square. So we can write that our flux phi of t will be equal to mu naught n I naught and pi a square sine of omega t. And because of this flux, we can find out the induced EMF in the shell. Induced EMF in the shell, that is EMF is minus d phi by dt, and this comes as minus t of dt. Phi we already know is our mu naught n I naught pi a square sine of omega t. So we get this EMF will be equal to minus mu naught n I naught pi a square omega cos of omega t, and we can easily find out magnitude. So its magnitude will be equal to mu naught n I naught pi a square omega and cos of omega t, and the resistivity is given to us which is given as rho, thickness is d, and radius is r, and length is l. So we have to find out its resistance. So now resistance of cylindrical shell. Resistance of cylindrical shell. So we have the resistance will be to the current will be nothing but the length of the current path, which is the circumference. Okay. So you can say from here the length of current path is our circumference, which is 2 pi r, and cross-sectional area of current flow cross-sectional area of current flow will be equal to A d multiplied by L, where d is the thickness and L is the length. Therefore, resistance of shell, if it is given as R shell, is equal to rho length oblique area. So we get this as R shell is equal to rho 2 pi r divided by d multiplied by L. Here length is nothing but the, you can say, length of the current path. And now we easily can find out the induced current because we know the induced EMF and we found out the resistance. So we can find out, or write rather, induced current in the shell. Induced current in the shell, that is our I induced, will be equal to EMF divided by resistance of the shell. And we already know the induced EMF, so we substitute the value, we get I induced will be equal to, we have this as mu naught n I naught pi a square omega, and this comes rho multiplied by 2 pi r, and this comes as dl, and this is our cos of omega t. So we just can now make a minor adjustment. You can say I induced current will be equal to mu naught n I naught a square omega, and this comes d multiplied by L, and divided by 2 rho r, and here we have cos of omega t. And here pi and pi cancel out, and rest remains same. So this was our the induced current which was asked. Yeah, induced current in the, find the induced current in the shell. So these were the 3 questions, and these complete all the 3 questions. Thank you.